Okay, so let's talk about determinants. Now, determinants are matrices, but the determinant represents... Okay, so let's look at finding the determinant of the 3 by 3. These are square matrices, right? Okay, notice the straight lines around them? That means determinant. All the directions said was find, and then I see the straight lines, which means determinant. Now, I'm going to use the same method that I used when I was finding the determinant of a 2 by 2. There is a second method, but I'm not going to talk about that. Now, the method we just used said, look at the main diagonal, right? Multiply the other diagonal and subtract them. Well, if I do that, I miss these 4 numbers. I miss the 4, the 1, the 2, and the 3, if all I look at are the diagonals. So I don't want to do that. I don't want to miss them, because the determinant is the overall value of the matrix. So here's the deal. So we adjust the process a little bit. And so we don't play ping pong with our eyes. We are going to rewrite the first 2 columns of the matrix. And again, the only reason we do this is so we don't play ping pong with our eyes. Otherwise, that's a little bit of a challenge to have to kind of do that back and forth. So, first things first, we look at the main determinant, correct? And so the main determinant has a 2, a -5, and a 5. And when you multiply those, good, you get 50. Now, oh, by the way, -50. And by the way, when I rewrote these 2 columns, I created 2 other diagonals in the exact same direction as this one, with the same amount of numbers, 3. Do you see the 4, 3, and the 1? Yeah, that'll multiply to 12. Do you see the -2, 1, and 2? Good. That'll multiply to -4. This one only has 2 numbers. That's not it. That's not good enough. So, when I am working on finding the determinant, I can't have 3 numbers. I'm only allowed to have 1 number. So I need to combine them. I need to combine a -50, a +12, and a -4, right? So don't think too deep about this. What do you got? Good. I thought I heard it. -42. So we'll have -42 minus. And now we got to come up with the other number, don't we? Okay, so let's look. I have to look at this other diagonal now, don't I, in the other direction. There's a -2, a -5, and a 1, which will give us, good, +10. But same thing, when I rewrote those 2 columns, I actually gave myself 2 more diagonals in the exact same direction as this one, also with 3 numbers on it. So I see the 2, the 3, and the other 2, which gives us, good, 12. And I see 1 more diagonal, a 5, a 1, and a 4, which will give us 20. Excellent. And again, I need to combine these. I have a +10, a +12, and a +20. What will that give us? 42. Excellent. So I'm going to minus the 42, which will give me a -84 as the overall value of this particular determinant. Cool? Okay, let's look at problem 2. Again, we don't want to play ping pong with our eyes, so we are going to rewrite the first 2 columns just to make it easier on our eyes. No other reason. Just to make it easier on our eyes. Got it? Okay, so I'm going to erase this up here so I can give myself a little bit of space to work with. All right? Okay. So I'm going to look at the numbers in the main diagonal, which will be a 4, a 1, and a 4. So that looks like it'll be a 16, won't it? And remember, I've got the 5, 0, and -2 in that direction also, don't I? That will be, yep, 0. And then I have the -6, the 3, and the 5, right? Okay, what is that? Good, -90. And when you combine these three numbers, what do you get? Yes, -74. A +16, a -90, and a 0. Cool? Okay, so I have -74 minus, and now I got to figure out the other number. So we have the 5, the 1, and the 5, which will give us 25. We have the -6, the 0, and the 4, which will give us, that's right, that one gives us 0. Kind of like having zeros in there, don't you? And again, the 4, the 3, and the -2, which will give you, good, -24. And when you combine these, that's right, you get a +1, which means the overall value of this particular determinant is a -75. Are y'all with me on this? Okay, again, you rewrite the first two columns so you don't play ping pong with your eyes. Now, determinants help us solve systems of equations. So hang in there. I'm coming up with Kramer's rule, which is going to use these determinants to help us find x's and y's and even z's. Okay, so let's talk about Kramer's rule. Kramer's rule is going to use determinants in order to solve for our variables. Now, this is a generic system of equations, and my variables are x and y. Got it? A and C and B and D, they're just coefficients of those x's and y's, so understand that. Now, Kramer's rule says you're going to set up a determinant for each variable. Well, how many variables do I have over here? I got 2. I have an x and a y. But Kramer also says besides those you set up for the variables, you need to set up one more for the main determinant. It's with respect to no variable whatsoever. Okay? All right, so let's take a look at this. So according to Kramer, I'm going to set up a determinant with respect to x. Now remember, determinants are square matrices, right? You can only find the determinant of a square matrix. So, based upon how many terms I have here, what's the largest matrix I can set up? Yeah, 2 by 2. I can't set up a 3 by 3. I don't have enough information for a 3 by 3, so that's not going to happen. So we're going to set up a 2 by 2. And the first column is still x, and the second column is still y. Now, for you English majors out there, are you able to define a word by using that word in its own definition? Yeah, no. You don't have to be an English major to remember that. So, I'm trying to define x, which means I'm not allowed to use my x's here. I'll be back to that x column in a second. So let's look at the y column. In the y column, I can put b and d because I'm not trying to define the y's. So I'm going to put b and d. Now here's the deal. If I can't use x because I'm trying to define x, and I already used the y's, what's the only thing left for me to fill in? Yeah, the E and the F in the X column. Got it? Okay, let's look at the matrix with respect to Y. Okay, again, it's going to be a 2 by 2, and the first column is X and the second column is Y. So, I'm trying to define Y. My first column is X. Am I allowed to put the X's in this first column? Yes. Because I'm not trying to define x, so I can use x. No problem. Second column is my y's. Am I trying to define y? Yes, I am. I use the x's. I can't use the y's, which only leaves me, good, it only leaves me that E and that F. Got it? Okay, one more determinant for us to set up, and that's the main determinant. And yes, still a 2 by 2. First column is still x, second column is still y. So, since there is no variable here, that means I can use my x's because I'm not trying to define x. So I can use the a and the c. I can even use the y's because I'm not trying to define y. Good? All right. Last but not least, Kramer's rule says this. Now that you've found these three determinants, here's how you find x. To literally find the value for x, take the determinant of x and divide it by the main determinant. To find the value for y, take the determinant with respect to y and divide it by the main determinant. Cool? All right. So, here we go. Let's put it into practice. Here's an example for us here to work on. Now, one thing I forgot to mention over here. You need to make certain your equations are a certain order. You need to make certain all the variables are on one side, alphabetically, and all the constants on the other. Because that was a setup over here. Well, is that true here? Are all the variables on one side of the equal to sign in alphabetical order? And are the constants on the other? Yes, they are. Okay, which means it's time to find my determinants. How many are we going to find? One for x, one for y, and then the main. Good, so there's 3 determinants to find here, right? Okay, so let's find the one with respect to x first. All right, it's going to be what order, what size? Yeah, 2 by 2, because that's the most I can fill in. So my x column. Can I use x's in it? No, I can't, because I'm trying to define x. What about these y's? These y's go in the y column. Can't use x, already used y, which leaves me, leaves me that 7 and that 10. So that means we're going to have 14 minus that negative 10, right? Which gives me a value of 24. Cool? Okay, let's find the determinant with respect to y. Again, first column is x, second column is y. So I'm trying to fill in the x column. Am I allowed to use my x's in the x column? Yes, because I'm not trying to define x. So I can use that 3 and that 2. Can I put the y's? No, because I'm trying to define y. I can't use the y's. I used the x's already, can't use the y's, leaves me these 2 numbers at the end to use. I don't have a choice. Okay, so let's figure it out. 3 times 10, so we have 30 minus 7 times 2. Good, 14, which leaves 16. Good. Okay, one more. The main determinant. So, the main determinant, x is first, y is second. Am I allowed to use the x's? Yes, because I'm not defining them, which means we have the 3. Whoops, don't need that little line there. Sorry about that. Okay, so we have the 3 and the 2 in the x column. And the y's? Yep, we have the negative 1 and the 2. So, let's find the determinant. 3 times 2? Yep, 6 minus 2 times negative 1. Negative 2, which leaves us 8. Good? Okay, so now, we're not quite done because Kramer says this is the way to actually find the value for x. So I need to take the main determinant, or the determinant of x, which was 24, and divide it by the main determinant, which was 8. So in this case, we get x equals 3. And to find y, I have to take the determinant of y, which was 16, and divide it by the main determinant, which was 8, which means y equals 2. Which means in this particular case, we have the solution of 3, 2. It's a consistent solution and it's independent. Remember those words. It's a consistent solution and it's independent. Are you with me? Okay, I got another example. So, let's kind of go over this one more time. Kramer's rule says you need to have square matrices in order to solve a system of equations using determinants. We have to make sure our equations are in the correct order. Okay, all the variables on one side alphabetically, all the numbers on the other side that don't have a variable with them, right? And then we set up a determinant for each matrix. So like in the first problem, we set up a determinant for x, we set up one for y, and those were the only two variables we had. And then we had to set up the main determinant, which was with respect to no variable whatsoever. Cool? Okay. Now, let's work on a second example with Kramer's rule and see what we get. All right. So our second example is going to look like this. Okay, is it in the correct format? Yes, it is. My x's and y's are on one side alphabetically. The numbers with no variables are on the other side of the equal to sign. How many matrices are we going to set up? Good, 3. One for x, one for y, and then the main determinant. And these matrices need to be, that's right, square matrices. So let's set up the one for x. And it's going to be a 2 by 2 because that's all the information I have. I don't have enough to fill in a 3 by 3. So first column is x and the second column is y, correct? Okay, so your x's go in the first column. Oh yeah, no you can't, right? Because you're defining x. Can't use the x's. And the y's will go in the y column, which means, yeah, that 3 and -5 need to fill in the x column, don't they? I can't use x, already use y, which leaves me the 3 and the -5 to fill in the x column. So let's find this determinant. Main diagonal, that's right, 3 times 4, which is 12, minus 5, right, -5 times -2, which is, yep, -10, which will give me a positive 22, won't it? Right? Okay. Now let's set up the one for y. Remember, first column is still x. Second column is y. So let's fill in the x column. Yes, I can fill in the x column with my x's. So 7 and 14. Can I fill in the y's? Nope, can't do it because I'm trying to define y. Which means, that's right, fill in the 3 and the -5 instead. So let's see what we get. 7 times -5, good, -35 minus 3 times 14, yeah, that's 42. So that looks like it's a -77, isn't it? Okay, last one, the main determinant. First column x, second column y. Can I fill in the x's? Yes, I can, because I'm not trying to define x. There's nothing here. Y's, yep, can fill in the y's because I'm not trying to define it. So let's see. 7 times -4, good, -28, minus 14 times -2, -28. Uh-oh. -28 plus 28, 0. Yikes! Uh-oh. Remember, that D, that main determinant, goes on the denominator, doesn't it? That means you're trying to define or divide by 0, doesn't it? Can you divide by 0? Nope, can't divide by 0. So, you know what this means? This means when the main determinant is 0, this means no solution. That's what that means. That means no solution at all. None at all. This system has no solution. This system is inconsistent. It's still independent, but it's inconsistent because it has no solution. Now, let me give you something for you to write down in your notes. If every one of these determinants had a value of 0, every one of them, if this 22 was a 0, if this negative was a 0, and this is a 0, if all three of these were a 0, I would have a dependent system. I would have an infinite number of solutions. Cool? Okay, so hang in there. We got 3 equations and 3 unknowns coming up for Kramer's rule. Okay, so let's look at this third example. Still solving by Kramer's rule. Got it? Okay, so how many determinants am I going to need to establish here? Good, 4 of them. 1 for x, 1 for y, 1 for z, and then the main determinant. Okay, so what size will be these determinants? Excellent, a 3 by 3. I can make it 2 by 2, but I want them as large as possible because I need to use as much information as I can. So they are going to be a 3 by 3. So let's establish the one with respect to x first. So remember, first column is x, right? So am I allowed to use x in the x determinant? No, I have to use these answers over here. Okay, next column is y. Am I allowed to use the y? Yes, I am, because I'm not defining y. And last column is z. Yes, I can use the z because I'm not defining z. So, now, you do your work on this. I've already done mine. And hopefully we agree. On this one, I have that the determinant is equal to 90. So hopefully we agree with that. All right, let's look at the next one, which will be dy. And first column is x, correct? Am I allowed to use x? Yes, I am, because this is a y, right? You can't use the y's and the y's. But I can certainly use the x's. Next column is y. Can I use the y values? Nope, can't use them. So I have to go to the ones at the end, the answers, shall I say. And last column is z. Can I use my z's? Yes, I can, because I'm not trying to define z. Okay, so you do your work. I've already done my work. And on this one, I ended up with a negative 54. So hopefully we agree. Now, let's look at the next one, the one with respect to z. Okay, first column is x. Can I use the x's? Yes, I can. Next column is y. Can I use the y's? Yes, I can. Last column is z. Can I use the z's? No, because I'm trying to define z, so I can't use the z's, which means I have to use those answers that are on the other side. And you do your work, verify mine. I got this answer to be 0. Good? Okay, so last one, and that's the main determinant. Am I trying to define x, y, or z? No, so I can use all my x's, y's, and z's. So x's are the first column, y's are the second column, and z's are the last column. Okay, and when all is said and done, I got a 30 on this one. Now remember on that second example, if the main determinant was a 0, it was undefined, right? If all the determinants were 0, that was the infinite number of solutions. Well, I got this guy being 0. This is not the main determinant, and not all of them are 0. It just means just this one variable, pretty much this one variable is going to be a 0, which is definitely allowed. Your main determinant, if that's 0, that means you got the no solution. Got it? Okay, so let's check it out. I still have to identify my answer for x. So x is going to be dx, which is 90, over the main determinant, which is 30. So in this case, we have x equaling 3. Y is going to be dy, which is negative 54, over 30. And yes, when you reduce this lovely fraction, you end up with negative 9/5. And last but not least, z will be dz, which is 0, divided by 30, which is just 0. So your ordered triple will be 3, negative 9 over 5, and 0. This system is a consistent system, and it's an independent system. Cool? Y'all with me? Okay, so we have some applications we're going to work on, so hang in there. Be right back. Okay, so let's talk about properties of determinants. Now, these properties help when I already know the value of the matrix, I already know its actual determinant, and if we switch a couple of rows around, we don't want to have to recompute the whole thing. These properties will help us not recompute the whole thing. So, let's look at them. The first property says if you have two rows or two columns and you switch them, you interchange them, the value of the determinant changes signs, which means basically you take the original number and multiply by a negative 1. The second property says if any row or column is multiplied by a non-zero constant, the value of that determinant is also multiplied by that constant. And last but not least, if any row or column is multiplied by a non-zero constant, and then you add it to another row or column, the value of the determinant remains unchanged. Basically, you're multiplying by a positive 1. So let's take a look at this first example. It asks us to find the value of this particular matrix knowing the determinant of this one is negative 6. So we know the determinant of this one is negative 6. What we're trying to find out is, did anything happen from this original one to the new one? And so let's see. UVW is supposed to be the first row. Oh, it's no longer the first row, it's the second row. So it went there. 648 is supposed to be second row. Oh, wait, it's not second row. It went to first row. UVW stayed the same place. So what happened? Yeah, we had two rows switch. And by the property, that means I take this negative 6 and I multiply by a negative 1. Did anything else happen? No. So in other words, the value or the determinant of this new matrix is 6. I don't have to recompute. I just multiply by negative 1, the original value, and here we go. Cool? Okay, let's look at this next one. Again, they want me to find the value of this matrix, knowing the determinant of this one is a 7. So let's see if anything happened. My first row is UVW. Well, it's still UVW. That didn't change. My second row is negative 4, 3, and negative 9. Huh. That's not in the second row. It switched, didn't it? As a matter of fact, it should have been down here, huh? Okay, hang in there. We'll figure that out in a second. My third row is XYZ. Well, it looks like it went to the second row. So it looks like two rows switched, didn't they? So that means I'm going to multiply this by a negative 1. But you know, this negative 4, 3, and negative 9 row, it didn't stay that, did it? It looks like they took this row and did what to it? It looks like they multiplied it by a negative 2. That was the only way we were going to get a 8, a negative 6, and a positive 18. So if they multiplied that row by a negative 2, that means I have to multiply this by a negative 2 also, which means this has a determinant value of 14. Cool? Making sense? Okay. Let's look at the third one. So let's look at this third one. 537 is supposed to be the first row. Well, looks like it went to row 3. UVW is supposed to be the second row. Well, looks like it went to row 1. XYZ is supposed to be the third row. Well, looks like it went to row 2. Huh. Okay. All right. Hold on just a second. So it looks like from here, it looks like UVW went to the first row, 537 to the second row, and XYZ, which means it looks like there is at least one row switch, right? So if there's at least one row switch, this is going to get multiplied by a -1. But from here, it looks like UVW stayed in the same spot. It looks like the XYZ now went into the second row, and the 5, 3, 7 went to the third row, doesn't it? Okay, so they did another row switch, which means -1 we have to multiply by. Okay, but what I'm noticing is UVW has this 4 in front of it. So it looks like this row got multiplied by 4, which means this also gets multiplied by 4. Are you with me? Okay, and last but not least, I know you're noticing this x minus 10 and minus 6 on the y and minus 14 on the z. Okay, so check it out a second. It looks like the 5 and the 3 and the 7, it looks like they all got multiplied by a -2. Because if you take 5, 3, and 7 and multiply by -2, you get the -10, the -6, and the -14, don't you? And then it looks like those numbers got added to the XYZ. Huh. Well, according to that third property, nothing changes. We multiply by a 1. It looks like XYZ got added to these guys. So, let's see. This looks like we are going to get a +3 and a -4, which looks like we're going to get a -12 for our determinant in this case. Cool? It's this third one you got to be careful of, because this row did get multiplied by -2, but they didn't change the 5, 3, 7. They multiplied it by -2, and then they took the XYZ and added it to it. Okay? All right, let's look at one more example. So, my original value is 6. Let's see what they did. Okay. XYZ didn't stay on the top, did it? It went to the third row. UVW went to the top. So let's see. UVW went to the top. XYZ, and then 2, 1, 3. That is one row switch at least. But then it looks like the XYZ went to the bottom, didn't it? And the 2, 1, 3 went to the middle. So UVW still at the top. 2, 1, 3 in the middle, XYZ on the bottom, which means another row switch. So another multiplication of -1, yes? Okay. It looks like, let's see, it looks like XYZ got multiplied by 3, didn't it? Well, then this guy's going to get multiplied by 3. Okay, and last but not least, let's see if you catch it. It looks like 2, 1, 3 got multiplied by a -1, but then it got added to this first row, didn't it? Which means nothing changes, does it? So it looks like the value of this determinant is 18. Okay. Hopefully these last two, especially these last two problems, made sense to you. Be careful of those properties. You have fun with determinants, and I'll catch you on the flip side.